This is question 4 from the Learning Outcome 3 notes for the unit Statics. And in this question, we've been asked to use Bose notation in order to analyse each of the members of this structure to determine the internal forces and the nature of these forces in each case. And the approach we're going to take to solve this question is to analyse different nodes within the structure and use this analysis with Bose notation in order to determine the information we're looking for. We'll start off the question by making a table that has the list of all forces and the information we're going to be recording about them. So if we have a look here, we have all the possible members in the table. We're going to have AB, AD, BC, BD, CD, and DE. And I've just listed these alphabetically as they appear on the table. AE is not a member, that's just a gap between two nodes on the support wall. When we do this problem, each of these members will be represented by a vector. These letterings will come from our spaces between forces, and we'll get to that shortly. We'll also be able to find the magnitude of each force in kilonewtons. And we'll also be determining the nature of each force. In this case, we're usually looking to see if a member is a tie or a strut. There's very rare cases, which we won't encounter in this question, of a redundant member that had no force acting on it, but in this case we'll find that they're all ties or struts. So we've got our table set out, and we're going to begin by analysing node C. And the reason for choosing node C is because it's the only node where we know something about one of the forces acting on it. So node C is this node I'm circling in green just now, and we'll draw in the lines of the forces and put the heading here for node C. And that's going to be represented by, we'll have a downward force, that's some kind of applied load of 16 kilonewtons, and then we have members acting horizontally to the left and up at an angle. And that angle, because the triangle BDC is an equilateral type triangle, this angle is 60 degrees. Now we need to have names for all of our spaces in this structure, because we can't use the lettering of the nodes. These don't correspond to the spaces, these correspond to the nodes. So we're just going to choose arbitrarily this lettering here, P, Q, R, S, and T, so that every space in between forces is lettered with a different letter. This allows us on our space diagram for node C to indicate what the names of these vectors must be. So we're going to call our downward vector, the 16 kilonewton vector, we're going to call this PT because it's between the spaces P and T. We're then going to see which of our vectors has T as one of its side and use that as a starting letter for that vector. And so we can see that the member CD is between T and S, so we'll call that one TS. And then taking S as our starting letter, we want each vector to follow on with the end letter of one is the start letter of the next. Our final vector, which is corresponds to the member BC, is between the spaces S and P. So we make this one SP. And so we can see we've got SP, PT, TS, SP, they all follow on from one another, which is what we're looking for when we're drawing our vector diagram just now. So we can draw a vector diagram for node C because we have enough information, and that is the knowledge of one of the magnitudes and directions of a vector. So we're using a scale here, and we're using this for the whole question. So I'll actually just write this up at the very top here. Our scale will be 1 centimeter to 1 kilonewton. And as I often do in problems like this, although I'll do my best to measure the angles on the whiteboard, I'm going to cheat a little bit and take the actual answers from the course notes to keep this a bit more close to what you would actually find in your bit of paper, because the whiteboard, it's not the most precise for measuring small intervals like we'll be using here. But what I need is 16 intervals, which we're calling centimetres, acting down the way to represent our first vector. And we'll give ourselves a little cross here to begin as our starting point. And this is also where we know we need to get back to. And we need a complete circuit of forces here, because each node in a structure that is under static equilibrium is also itself under static equilibrium, which means there's no resultant force. These three forces will balance and come back to the starting point. So I'm going to just use a different colour of pen for every vector. There's no requirement to do this in a problem, but it maybe helps things stand out a little bit. So we're going to draw down 16 centimetres, so 4, 6, 8, 10, 12, 14, and that looks good to me, 16. And we'll indicate the direction of travel on this vector. We know it's acting down the way, and we can indicate the size as well, 16 kilonewtons. We can also indicate our start and finish points. Because we've called this vector PT, it means our starting point is P and our ending point is T. And this is just a convention that we've picked, but everything else will follow from here. So because we end at point T, we want to add our vector TS on at the point T. Now what we know from our space diagram is that TS is a horizontal line. So we set our ruler to being completely in line with the horizontal part of our page. And we're going to draw a line that connects to the end of this vector. Now Bow's notation tells us that we just draw a line off in both directions. Now we might have a gut instinct here that we should be going over to the right, because we can kind of think about where the next vector is going to go, but that's not our challenge at this point. Our challenge is just to draw a line that's horizontal, as long as it touches the end of PT, so that's our point T. Somewhere along this green line is the point S, which will form the other end of the vector SP. So going back to point P, we know the vector SP needs to join up to point P, and we also know that it needs to come down at an angle of 60 degrees, because if it's going up to the left at an angle of 60 degrees, it means it's also going down to the right, measured from this horizontal line I've drawn in here at an angle of 60 degrees as well, using the alternate angle rule. So if I line this up here, I've just changed my pen colour again, I'll use a blue colour for this vector. I draw a point that's going to be joining our crosshair to our green vector. Now at this point, I could want to rub out the extra bits of line we don't need. It's not really essential to do this because we know this is not part of the vector, but let's tidy things up a little bit. So this is our vector diagram, and to complete the diagram, we need to do two things. One is to indicate the direction that all of the vectors are traveling, and two is to measure the vectors so that we can get their length in centimeters and translate that back into kilonewtons. Now, in each case, because this is a vector diagram, we have a vector path that takes us from the start back to the start, round a circuit. So as we come down our red vector, down to the green line here, the vector T, and I should have indicated that means this is point S here. The only way to go to get to the next part of the circuit is to travel to the right. And that means that the vector TS, so the member that that's representing, is going to be the internal force pointing towards the node, which means that the external force is compressing this member, so this is going to be a strut. We'll get to that in a second. We continue to follow the circuit round, so we've come down the red line, we've gone right across the green line. It means to get back to the start, we have to go up the diagonal blue line, back to the start. I can mark this on our space diagram on the left-hand side as well. And because the arrow is pointing away from the node, that means that this is going to be a tie. And before we go and mark all of this on our little table at the start, we're going to measure these things. So if I measure off on the vector SP, that comes to about 18.5 centimeters, which is, of course, if we on a 1-to-1 scale, 18.5 kilonewtons. And we'll measure again the other vector, so get our ruler horizontal. And we can see this is going to measure 9, and it's hard to see this, it looks bigger than 9¼ less than 9¼ here. But we'll go with the answer from the course notes because we want to keep that consistent, and that gives it an answer of 9.2. So it's just less than 9¼ centimeters, 9.2 kilonewtons. So if you're drawing this in a 1-to-1 scale, you should be measuring something close to 9.2 centimeters for that vector. So that's our analysis of node C complete. We can take this over here to our table. So what have we said? We have said that BC is represented by the vector SP or PS. It doesn't really matter on the table which way around it is. And we've said that DC or CD is represented by the vector TS. We found out that BC was 18.5 kilonewtons in magnitude, and we found out that its nature is that it's a tie because the internal force is pointing away from the node. With CD, we found out its magnitude was 9.2 kilonewtons and that its nature was a strut because the arrow, the direction of the force in the vector TS, is pointing towards the node, and that's an indication of a strut. Now, we don't want to crowd our original diagram too much, but we can make a few markings on this to help us with what we've learned. We'll leave the magnitudes off the diagram. We can read them from our table. But what we can indicate is that the vector BC, the forces act in the way, so away from the nodes that this member is joined to, and the member DC or CD, the forces act towards the nodes. So this is giving us some valuable information we're going to be able to use to do some nodal analysis on other nodes as part of this structure. So we can now look at node B, because with node B we have two members that we don't know anything about, but we have one member, the member BC, where we now have the direction of the internal force and its magnitude, and this gives us enough to draw a diagram on. And there's a method, and we'll be doing this in a separate video, where we could actually build this second diagram onto our existing diagram, but we're going to leave that for another video. In this video, we'll be tackling each node separately with a separate space diagram and a separate vector diagram. So let's have a look at node B then. Node B has, I'll put a little heading here. Node B has these lines coming into it. These are all representative of members. And we know something else about it as well. We know that this force on the right-hand side, the member BC, is acting away from the node, and we know it's acting away with a force of 18.5 kilonewtons. That gives us a starting point. I should have included the spaces in node C, so I'll add these in now just so we've got them for reference. And I'll put our spaces onto node B just now also. So our spaces above, we have space P. Beneath this line, we have space R. And in this triangle here, we have space S. So this will give us our names of our vectors. And we have to do this, I suppose, here because our diagrams are where we were able to use a diagram for node C, but down here, without going back and forth, we'll just use this. So let's name each of our vectors in turn, and we'll start off by naming our first vector. Now, it doesn't matter if we call it SP or PS here for the purposes of this diagram. So we called it SP last time, we can call it SP here as well. That means our next vector we're going to label is going to begin with P. So SP, next one begins with P, and our vector that has P in it is this one up here, PR, meaning our third vector will begin with an R, and that will be vector RS. And this is what gives our order for labeling. If we had called the first vector PS, we could have done SR and RP, and we could have drawn a diagram that would be a mirror image or a rotated image of the one we're about to draw, but all the magnitudes and all the natures would still have been the same. So as long as you make consistent choices with your labeling, your diagram's still going to work out either way. So let's have a look at this then. We must start again with a crosshair, and I think starting in the middle of our page here will be ideal. And we know that this is going to come down at an angle of 60 degrees because this angle in here is 60, and so is this one, meaning that this angle below the horizontal must be 60 as well. The three angles on one side of a straight line have to add up to 180 degrees. So we're going to draw an angle acting down from this horizontal line at an angle of 60 degrees. Now again, this is something you'd be doing with your protractor. The whiteboard ruler is able to do this accurately for me. So I'm measuring it downwards an angle of 60. I'm lining up the start of the ruler. Well, I'll move this to the top of the page. The start of the ruler with the crosshair, and I'm going to draw a line of 18.5 centimeters to represent that vector inside this internal force from the member BC, because we know from what we've learned already that the internal forces act away from the node. So we'll use red as our first colour here. 2, 4, 6, 8, 10, 12, 14, 16, 18, and a half, as accurately as we can. And what can we say about this? Well, we know the direction. We had this from the previous part of the question. It's 18.5 kilonewton force. If we wanted to keep ourselves right, we can remind ourselves it's a 60-degree angle. And then we can have a look at what we're going to do next. Well, we know this is the vector SP, so we're starting at point S and moving down to point P. So the next vector we're going to draw in is PR, the one that starts with the letter we finish with. PR is a horizontal line, so again, we'll make our ruler horizontal, and we can draw a line connecting to the head of our vector. Now, looking at our diagram, you probably have a strong indication that we need to go left with this line, but if you weren't sure, that'd be fine. We can just draw a line through across our page. But the reason I'm saying that I was feeling we'd be going left is that I can see the direction of the other vector RS, and I know that it needs to join up with that crosshair S. So I'm thinking it's going to be sloping down to the left, and indeed that is the case. If we were to extend our horizontal line from the crosshair, we're measuring down an angle of 60 degrees from here. And we know this, if we just highlight this here, because of this 60-degree angle that I've just circled in blue, that's telling us the orientation of the line RS. We know this line needs to end at the crosshair, and where it starts is where it's going to meet the green line we've drawn in representing vector PR. So again, we'll set our ruler to 60 degrees, this time sloping downwards to the left. I'll line this up with the crosshair, and at this point we know we need a line that goes through the crosshair and it goes through the green line, but it's really joining these 2 points. I'll use blue for this colour to join this up, and I can take the ruler away. And once again, we will follow the path of the vector. From our starting point, we travel along the red vector going down the way, meaning we have to come back to the left across the green vector, meaning that vector PR acts away from the node, meaning that member there is going to be a tie. And the path continues back up the blue vector to our crosshair starting point, meaning that this vector acts towards the node meaning that that member is going to be a strut. Now, at this point, what we should do is we should measure all of these lines. But if you are keen-eyed, you will have observed that all the angles in this triangle must be 60 degrees because of the angles that we've drawn in. And if all the angles are 60 degrees, this means that all the forces or the length of the sides have to be the same. And because we're doing a scale diagram, that means all the forces are the same. But by all means, if you're following along with this video, check your measurements, that these are all 18.5 kilonewtons. I'm not confident mine necessarily are, but they should certainly be if it's been drawn accurately. So I can say something now about these two additional forces we've learned about in terms of both their magnitude and their size. So let's go back to our table and remind ourselves what each one is. So we'll start off with the vector PR. Well, PR is this force coming out of point B to the left-hand side, and so that represents the vector AB. We've established its magnitude is 18.5 kilonewtons, and its nature, well, if we go back and look at what we've learned, the internal force for PR is heading away from the node, which means that this internal force must be a tie. We've also learned about the vector BD, which is represented by our vector RS, so we can mark this on here. RS, that's also 18.5 kilonewtons, and because the arrow is pointing towards the node, this must be a strut. And so we filled in the details about two more vectors in our structure. So all that remains is the members AD and DE. And just as I say that, I'm sure you can tell what they've got in common is they've got the node D in common. So we only need to consider one more node in this question in order to complete it. Before we do, though, we're going to mark on what we've learned about the remaining nodes. We've learned that BD is a strut and so has these internal forces, and we've learned that AB is a tie and so has these internal forces here. And it's BD in particular that we need the information about in order to solve our final node. So this one's going to be a bit of a tricky diagram, but we'll go through it. And again, this is another reason in the video where you might want to choose to pause at certain points. So node D is going to be our final node to analyze. So the forces at node D look like this. We have two horizontal forces connected to either side of the node, and we know that the direction of the one at the right is pointing in the way, and we also know this force angled down here is pointing towards the node, because both of these are struts because they're acting under compression. We'll get the lettering for our spaces. It's Q, R, S, and T. So let's get all of these in as well. Q, R, S, and T. And we have the sizes for two of these forces also. So our force acting down here, I just want to make sure I get all my lettering correct. BD is going to be 18.5 kilonewtons and CD is 9.2 kilonewtons. So we can say here, this is I'll put it in black. This is 18.5 kilonewtons and this is 9.2 kilonewtons. And this is the information we needed to analyze this node. We can't analyze a node where we have more than two unknown forces because we're relying on drawing those two forces connected to some other point of a specific length and direction and getting them to cross over and form the missing section in our vector diagram. So we're going to begin this by labeling again all of our vectors and then drawing in our diagram, but we have to start our diagram by drawing two vectors that we know. So that's why I'm going to start off by labeling our vector of 9.2 kilonewtons TS, and then I'm going to label this one as 18.5 SR. Now, this came up in class. We could, of course, have named that RS and the other one ST and added them in that direction. The direction is not important. Either way, you get a diagram that works. What is important, though, is that the vectors all follow each other. So TS goes to SR, goes to RQ, goes to QT. But we could equally have had TS, so we could have ST goes to TQ, goes to QR, goes to R. Mislabeled that, that's why. Oh yeah, it goes to RS. I should probably do that again. Look at this SR. Well, it's a bit more like an R. I nearly called it ST there. So we can label it either way around as long as we're consistent. That's the key. Consistency is the key, as I'll say many times in these examples. So let's start off by drawing in vector TS. Now vector TS is horizontal and it's acting to the left. So we'll start off with a cross here, and I think we'll just put it, I've got to be careful where this diagram goes and then, because I know it comes back in itself because of the two horizontal vectors. But we'll start here and we'll try to draw a vector that's 9.2 kilonewtons in length. So lining this up, or thereabouts, we have a vector, and we'll draw it 2, 4, 6, 8, 9, and that looks like about 9.2 to me there. And again, we know the direction because we've established this in the previous part of the problem, and the size is 9.2 kilonewtons. And this is the vector TS, so T is our starting point and S is the end of this vector. This means we can now draw in the vector that begins with S from the end of this, and that vector is SR, and it's going to be acting downwards from the horizontal at an angle of 60 degrees. So I've put in a very dodgy horizontal line there and mark down 60 degrees from it. I'm going to draw in an 18.5 kilonewton line to represent, and I think this is the member BD that we established in the last part of the question. So let's move this, just fits in my page if I remember correctly. So we'll line that up, and we're going to measure down 18.5, and we'll make this one blue. 2, 4, 6, 8, 10, 12, 14, 16, 18 and a half. And so that's our second vector. And for both of these vectors, we have the direction, we have the size, we can put 18.5 kilonewtons here, and that's fine. All that happens now, that was the point R, we're going to join our vector that begins with R to the end of the blue line, and our vector that ends with T to the end of the red line. And by doing that, we'll have a crossover point, which will give us the point Q, and it will allow us to measure the two remaining vectors. So let's have a look then, first of all, at the vector RQ. Now the vector RQ acts up from the negative direction of the horizontal with an angle of 60 degrees. That means if we have a little dotted line like this, we need to measure 60 degrees up from it, which is what we'll do. I accidentally added a note there, we're trying to remove that. So this is the vector RQ. We've got the end R, but it goes off in one direction to become the vector Q. Now, you might guess, and you'll be correct if you have, that it's going to be pointing up the way, but we don't need to make that assumption. We can let the drawing do its work for us. The other vector is the vector QT, which means it's going to join from the point T, which is actually already covered by this vector TS, and it's going to join from the point T to meeting our green vector RQ at the point Q. So we're going to change our pen color just now. We'll use a purple pen for this, and I'm going to draw in what, and this can be tricky in your diagram, especially if you're not using different colors, but it's absolutely fine to draw over the red line as well. And if you're doing this in a single color, as long as you've labeled each point with the letter, you'll be able to still see where vector TS is. So we take our pen and we draw, well, maybe this pen's slightly too thick, but we get the point here. We draw across to join with the green line. I'll definitely be changing the pen thickness of that. And that point where the purple and green lines intersect is the point Q. So that purple line is the vector TQ, and that green line is the vector RQ. And we can take from this, again, the directions and the magnitudes of our forces. So let's work out which direction things are going in first of all. Next, got to be careful here because we've got lines over lines, so but we can still see a little red arrow we began with. So what happens is we follow what would have been our red line from point T to point S. I'll just draw a little line below to indicate that direction. So we just come along here with our red vector. We to come to point S and come down the blue line because we know that's where we're going because that arrow is already on the diagram. There's no choice in the matter, and it has to join to a new vector. It can't join in the middle of the purple vector. When it comes down to the bottom at point R, it's going to travel up the green line this way, and then we're going to go back along the purple line all the way back to T. So we're retracing its path as it goes on the journey from S to T, but it's going from Q all the way past S and back to T. So we've completed our circuit, even if we've retraced some of our own steps, thinking about it as walking back through our own footprints as we get back to the point T. Again, looking at this, you can see that the triangle that's formed here, the green line, if we measure it, is going to end up being 18.5 kilonewtons as well. And again, you can measure that for yourself to convince yourself when you're doing this that's indeed the case. But in this triangle, we'll have 360-degree angles. So the blue line, the green line, and the part of the purple line between Q and S will all be the same. But of course, the vector QT isn't just that part of the triangle, it's a triangle plus ST. Now, again, we could be clever here as well and recognize that if ST is 9.2 and that part of the triangle is 18.5, then together they must be 27.7 because that's 18.5 plus 9.2. But equally, get your ruler, stick it up here and measure it out. And it's, in my ruler, it's somewhere close to 27 3/4, not accurate enough to measure. So I'm going to trust the course notes do indeed have the right answer, and we can call this 27.7 kilonewtons, which is great because we now have every force identified in terms of its nature and its magnitude. So let's go up here. So let's take QR first of all. So QR will put you on here. So QR is heading away from the node and QT is heading towards the node. So QR represents a tie, QT represents a strut. So we said QR represents a tie and QT represented a strut. We said that QR, which represents member AD, because the spaces on either side of line AD or Q and R had a magnitude of 18.5 kilonewtons. And we said from our purple line in the last one that the member DE must have an internal force of 27.7 kilonewtons. And that completes the example of question 4 from the course notes.